All right, hi folks, this is Larry Mussolino. I'm recording a video for Module 9 in Math 181, and this has to do with calculating probability and probability models. And we actually started discussing this in Module 8 as we were discussing relative frequency. So we want to extend that discussion and try to come up with some kind of different probability distributions. All right, well, let's take a look here at a quick example. Let's say I go out and survey 100 households, and I ask the question, how many dogs do you have in your household? So I get the answer. Some families say 0 dogs, other families say 1, other families say 2, a few families had 3 dogs. All right, well, here's the frequency table, all right, because I counted up the frequency for how many families own each number of dogs. I want to generate a probability distribution. Well, a probability distribution is really adding up, a probability distribution is really calculating the relative frequency for each one of these rows in the table. So the way I calculate the relative frequency for each row is I take the frequency for that row and divide by the sum of all the frequencies. Again, we talked about this in the last module. Well, for the first row, there were 35 families that had 0 dogs out of 100 families altogether. So the 0.35 or 35% of families own 0 dogs. But there's a couple of criteria that we have to meet in order for this relative frequency summary to be considered a probability distribution. First, every probability that we come up with in the right-hand column must be a number between 0 and 1. Well, that makes sense because anytime you calculate a probability, it always has to be a value between 0 and 1 inclusive. I can never have a negative probability. I can never have a probability greater than 1. The other criteria is if you add up all the probabilities, the sum of this column must add up to 1. So if you were to add up these probabilities, you would see they add up to 1. So these are 2 conditions for a probability distribution. If either one of these conditions is not met, then it's not a valid probability distribution. Okay, well, you might remember that the way you calculate these probabilities, there's really 2 ways to think about this. If you have a scenario where the outcomes are equally likely, this would be things like equally likely outcomes, you remember, are scenarios like, for example, flipping a coin, right? Because getting heads or tails, equally likely. Rolling a 6-sided die, because it's equally likely that each face of the die will be rolled, assuming it's a fair die. Selecting a card from a deck of 52 cards, right? Assuming the deck is well shuffled, you have a 1/52 chance of selecting any individual card. And many casino games are based on equally likely outcomes. If you think about a game like roulette, for example, if anyone knows the game of roulette, when you spin a wheel and a ball is equally likely to fall into any one of the 38 slots on a roulette wheel. So when you do have equally likely outcomes, here is the formula to use to calculate the probability. You take the number of outcomes for the event you're interested in and divide by the total number of outcomes. So here's an example. What if we want to know the probability of selecting a jack from a deck of cards? Well, I ask myself, how many jacks are there? There's 4 jacks. How many cards total are in the deck? 52. 4/52 is the probability of selecting a jack. Well, there's another rule that we can use, because you might remember that we might want to know the probability of A or B. Sometimes we write this as A union B. So you remember the formula was the probability of A plus the probability of B, but we have to subtract out the probability of A and B. In symbols, the word and would translate to the intersection symbol. So I could write this as A intersection B. And the reason you do the subtraction out here at the end is to avoid double counting. Because when I counted the probability of A, and I also calculated the probability of B, I might have double counted where an event is both in categories A and B. Okay. Here's a quick example. What if I want to know the probability of selecting a jack or a diamond? Well, I have to think about the probability of selecting a jack plus the probability of selecting a diamond, but I've got to subtract the probability of selecting a jack and a diamond. Well, for the probability of a jack, we already worked that out. That's 4 over 52. What about the probability of selecting a diamond? Well, there's 13 diamonds in the deck out of 52 cards. What about this last probability of selecting a jack and a diamond? Is there any way, or how many ways are there to select a card that's both a jack and a diamond at the same time? Well, there's only one way. There happens to be a card that is the jack of diamonds. So by selecting that one card, you're selecting a card that's both a jack and a diamond at the same time. There's only one of those cards, so that would be 1 over 52. So when we plug that into the probability formula here, we're getting the answer 16 over 52. Okay. Again, folks, of course, there are good videos to check out here in the lecture notes, so please be sure to do that. All right, well, in Module 8, we talked about counting using permutations and combinations. So when it comes to finding the total number of outcomes, we might need to use permutations or combinations to come up with that answer. That's why we were interested in studying permutations and combinations, because sometimes it's useful to know the total number of outcomes. Okay. All right, let's do a quick example here. Let's say you want to know the probability of winning a lottery, where to win, you've got to select 5 numbers out of 50 total. Okay. Now remember, usually the order of the 5 winning numbers does not matter. So I want to work this out and figure out the total number of outcomes. So really the total number of outcomes are how many ways are there to select 5 numbers out of 50 when the order doesn't matter? Well, that's combinations when order doesn't matter, if you remember. So we would be figuring out the combinations of 50 5 numbers at a time. And if you work this out, the answer turns out to be a little over 2 million. So the probability of winning this lottery is 1 over 2 million. The reason it's a 1 on top is there's only one way to win the lottery. You have to pick the exact correct winning number. So there's one way to pick the winning number out of 2,118,760 possible combinations for lottery tickets. And so that probability is a very, very small probability. And of course, that's why it's almost impossible to win the lottery. The probability is a very, very small number. All right, so why don't we go and do a few WebAssign examples to work through some of these formulas. Hold on, let me bring up WebAssign. Hey folks, I have the Module 9 homework here. So let's work through a few examples here. And I want to focus on those examples that don't have a watch it, because remember, this watch it button brings up a short video which explains how to work through a problem. So I'm going to let you make use of that resource. I'm going to focus on some of the others. Let's go to number 2. Number 2 says calculate P of E using the given information. Well, if you remember, the formula to find the probability of E is put the number of outcomes for E divided by the total number of outcomes. Well, they're really giving me the 2 numbers here to plug in. The number of outcomes for E is this number 4, and the total number of outcomes is this S. Remember, S is the sample space. So N of S is giving you the number of elements in the sample space, which is the same number of elements in the sample space, which is the same as the total number of outcomes. So that's 4 over 16. I can simplify that to be 1/4. All right, let's go down to number 3. Number 3 is really the same idea. We're going to use the same formula. Number 3 says, what is the probability of E? Well, I'm going to take the number of outcomes for E. That looks like there's 4 of them. Divided by the total number of outcomes in the sample space, it looks like there's 5 of them. So that's the answer here, 4 over 5. All right, let's go to number 4. Number 4 is asking you a question about a probability experiment of rolling 3 coins. And you want to know what's the probability of rolling more heads than tails. All right, well, maybe one thing I could do is list out all the possible outcomes. So let me toss coin number 1, coin number 2, coin number 3. Now, I know there's 8 possible outcomes here. How do I know that? Well, there's 2 ways for coin number 1 to come up, either heads or tails. There's 2 ways for coin number 2, and there's 2 ways for coin number 3, 2 outcomes for each of these. Multiply these together, I get 8 outcomes altogether. So there's going to be 8 rows in this table. All right, so let's list them out. One easy way to list them is go to this first column and list 4 heads, then 4 tails. Then you go to the next column and list out 2 heads, 2 tails, and then go to the third column and alternate heads, tails, heads, tails, and so on. All right, now I've listed out all the 8 outcomes. I'm going to look at each row. Where is a row where there's more heads than tails? Well, this first row, there's 3 heads, 0 tails. The second row, there's 2 heads, 1 tail. The third row, there's 2 heads, 1 tail. The fourth row is a no, because the fourth row, there's only 1 head and 2 tails. So there's actually more tails than heads for that row. All right, how about the fourth row? Yes, there's 2 heads and 1 tail, so there's more heads. The fourth row is a no. This row is a no, and the last row is a no. So it looks like the probability of more heads than tails, there were 4 rows where that occurred out of 8 rows altogether. So this probability is 1/2. All right, so in this case, I just had to recognize that there were 8 outcomes total, and then I just counted up how many of those 8 outcomes met this event I was interested in where there's more heads than tails. All right, let's do a few more. Let me go to number 5. All right, so number 5 is giving me some different probabilities. They're asking me to find the probability of A union B. Well, we just talked about a formula for this. It says the probability of A union B is the probability of A plus the probability of B minus the probability of A and B occurring together. And remember, when you see the word and, it's the same as an intersection symbol. In fact, I'm going to use an intersection symbol here just to be consistent. So this is the formula. Well, they're really giving me everything to plug into this. The probability of A was given as 0.1, the probability of B is given as 0.4, and A intersection B was 0.05. So this is 0.5 minus 0.05, which is 0.45 for that one. All right, let me go to number 6. Very similar. I'm going to use the exact same formula. But now they're asking us to find the probability of A. All right, well, they're giving us the probability of A union B. That's given to us as 0.9. P of A is the unknown, so I'm just going to leave that alone. The probability of B is given as 0.8, and this probability of A intersection B is 0.7. So this is an easy calculation to solve for the probability of A. On the right-hand side, 0.8 minus 0.7, that's 0.1. And the last step here is I'll subtract 0.1 from both sides. So it looks like probability of A is 0.8. So again, I use the same formula as we did in problem 5. It's just that the unknown quantity here was the probability of A. All right, well, let's go to number 7. Number 7 is giving us the probability of A and asking us to find the complement. So remember, when you see A with the apostrophe, that's really the probability of not A. Sometimes we say A prime. Well, that's 1 minus the probability of A. That's called the complement rule. So that's just 1 minus 0.66. So the answer on this one is 0.34. All right, let's do a few more. Let's go to number 8. Number 8 is telling us that these events are mutually exclusive. Well, there's a rule that when events are mutually exclusive, it's called the addition rule. We could just add together the probability of A plus the probability of B plus the probability of C. Remember, mutually exclusive means these events cannot happen at the same time. For example, the probability of A and B happening is 0. Right? If they tell me it's mutually exclusive, that means the events cannot happen together. So for mutually exclusive events, we know that the probability of A and B is 0. Well, this is just adding together the probabilities they gave me. 0.1 plus 0.5 plus 0.3 works out to be 0.9. All right, let's do a few more. Let's see, number 9 has a watch it. Let's go to number 10. All right, so number 10, they're giving me this table. And part A of this question says, find the probability that a randomly selected mortgage was not in foreclosure or repossessed. All right, so what events then are they asking me about? Well, they want not foreclosure and not repossessed. So that really leaves me just current and past due. Well, I'm going to calculate a relative frequency. So the probability of current and past due is just going to be adding up these numbers, 126,330 plus 53,310 divided by the total, 193,480. And you can work this out on your calculator. All right, let's go to part B. Part B says, what's the probability that a mortgage was not current? All right, well, not current means it's either past due or in foreclosure or repossessed. So I'm going to ignore the current because they're asking me the probability of not current. So I'm just going to add up the past due plus the foreclosure plus the repossessed and put that all over the total, and this will be the answer. Another way I could have worked out part B here is to find the probability that a mortgage is current. That would be 126,330 over 193,480. Then to find the probability of not current, I could just take 1 minus the probability that it is current. So I could use either one of these two methods for part B. All right. Maybe we could do a few more. Let's go to number 11 here. All right, let's see number 11. It says in 2014, the probability, in 2014, the probability that a randomly chosen electric car was manufactured by a certain manufacturer is 0.36. The probability it was manufactured by a second manufacturer was 0.44. What's the probability that it was manufactured by neither company? Well, really, let's think about it this way. The probability that it was manufacturer 1 or manufacturer 2, we could figure that out as just adding these two probabilities together. which would be what, 0.80. Well, the probability that it's not these manufacturers, not manufacturer 1 or manufacturer 2, is really the complement. So I could just work out 1 minus 0.8. So there's a 20% chance that the car was manufactured by neither company. All right, let's take a look at a few more here. Let's go to number 12. So number 12 is giving us a table with SAT scores and broken out by admitted versus non-admitted students. All right, now the key to these problems is really reading very carefully and trying to understand what numbers in the table correspond to the event you're interested in. And then to find the probability, you'll take the number that corresponds to the event you're interested in divided by the total. In our case, the total is 70,139. All right, so let's read carefully. It says an applicant did not have a math SAT score below 700. Okay. Well, if they did not have an SAT score below 700, they're really telling me to look at this column right here. Now, they're not telling me anything about admitted versus non-admitted. So I've got to include both of these numbers, right? So to not have an SAT score below 700 means you had an SAT score above 700. So the probability for this event, E, is going to be adding up these two numbers that I circled and dividing by the total, 7139. I'll do this on my calculator just to work this out. So the top of this fraction is 24,997. And if I work this out on my calculator, I'm getting the answer 0.36 when I round to 2 decimal places. All right, so again, the key is reading carefully to understand exactly what conditions from the table meet the event that you are interested in. All right, why don't we do number 13? This one's a little trickier in a similar kind of table. But number 13 says, determine the probability that an applicant did not have a math SAT score of 400 above and was not admitted. All right, so it says not 400 and above. Well, that means I've got to cross out all of these numbers, right? If you didn't have a math score of SAT or 400 above, it means you had an SAT score below 400 and was not admitted. Well, this is not admitted right here. So the only condition or the only cell in this table that meets the event is this 1652. So this probability is going to be 1652 over 7139. If you work that out on your calculator, I think you'll get 0.02. All right, so I had to read this very carefully to understand the two conditions that were being given, and using that, I can determine which values, which numbers from this table are applicable to the event E that I'm interested in. All right, let's look at a few more. How about if we do, let's do number 16 here. It says your company has patented an electric padlock with a 3-digit code. Each digit can be 0 to 9 and repetitions are allowed. The padlock is designed to open either if the correct code is keyed in or if exactly one of the digits is incorrect. What's the probability that if you randomly pick 3 digits, you'll get the correct code to open up this padlock? All right, well, let me start to organize this. I'm going to think of this as kind of like 3 boxes here. These are the 3 digits. And let me first ask myself, what is the total number of outcomes for this experiment? Really, what's the total number of possible 3-digit codes? Well, each digit can be 0 to 9. That means I can really fill in each box 10 ways. Well, you might remember the fundamental counting principle says multiply these together to get the total number of outcomes. So the total number of outcomes is 1,000. All right, so I know that's going to be the denominator of my probability. All right, now let's think about the event of getting a code that opens the padlock. All right, well, there's two possibilities. You either guess the correct 3-digit code, or you get correct 2 out of the 3 digits. Right? Either one of these will open up the padlock. Let me call this scenario A, and I'll call this scenario B. All right, what's the probability of getting the correct 3-digit code? Well, there's only one way for that to happen. You'd have to get the exact correct 3-digit code. There's only one of those. So there's one way for that to happen. But event B is a little trickier. What if you want to get 2 out of 3 correct? Well, let me think about the different scenarios for that. Here's what can happen. I can get this correct, and this wrong. That's one way. Or I could get this correct, and the middle digit wrong. Or I could get the first wrong and the next 2 correct. Either one of these 3 possibilities would get the correct 2 out of 3 digits, and the padlock would open. So let me figure out how many ways are there for this to happen. Well, for the correct digit here, there's only one way for that to happen. I have to get the correct first digit. There's only one way for this correct second digit. How many ways can I get the 3rd digit wrong? Well, I'm thinking, I'm going to make this one way here just to make it clear that what I'm talking about here is one way. It turns out there's 9 ways to fill in this wrong digit. The reason there's not 10 ways is that the 10th way would include the correct digit. But I've already counted the correct digit in this first event. So that's why there's only 9 ways to get the wrong digit. That one other digit that I'm leaving out is the correct digit that goes in that position. Well, the same thing here. There's going to be 1 way for this box, 9 ways to fill in this box, and 1 way to fill in this box. And again, there's 9 ways for this, 1 way here, 1 way here. So this is 9 ways. Remember, you multiply these number of ways together. 9 ways for this first row, 9 ways for the second row, 9 ways for the third row. Altogether, that's 27, but I've got to add 1 more for event A. So altogether, there's 28 ways to get the correct code. One of those 28 ways is getting all 3 digits correct. The other 27 ways is one of these scenarios where you got 2 out of the 3 digits correct. So the final probability here for opening the padlock is there's 28 ways out of 1,000 total. So this is the answer. I could simplify this fraction by dividing top and bottom by 4, 7 over 250. All right, folks, hopefully this is helpful in getting started. Please remember to use the watch it here, folks. Also, please remember that if a WebAssign problem says hint, see example 4 or something like that, go into the textbook and look at that example they're referencing, because that example is showing you a similar worked out problem to the WebAssign question. All right, let me know if there's any questions, and hopefully this is helpful as you're working in Module 9.